plane stress transformation. And what we're doing is we're looking at only stresses in the same plane. And what I mean by that, by plane stress, is, well, it has two normal stresses and one shear stress. Okay? And what we're trying to do here is basically take those stress components and basically orient them in a different way, transform those stresses so that basically finding stresses in different directions from the specific stresses that we have. So the sign convention we have for something like this would be, again, both tension. So I've got normal stress and in the x and the y direction, and then my shear stress is defined as up on the right side to the right on the top side. We're calling that a positive shear stress, and a positive angle to be counterclockwise. Okay, so that's what we're calling our sign convention here. Okay, so this is an element in plane stress. Again, two normal stresses and one shear stress. Okay, now in order to transform this, what I'm essentially doing is finding what the stresses are at a certain angle. So I can section my element here at a specific angle, and I have this new stress, sigma x prime, and new shear stress, tau x prime y prime. Okay, and what I do is I essentially sum the forces in these new directions, the x prime and the y prime direction. So in the x prime direction, I have my new stress, delta A. Okay, and then I have components of all of these stresses down here, and that's really what I have on each one of these. And I'll let you go through those on your own. Once I simplify that and I solve for the stress in the x direction, I get something that looks like this. Okay, basically all my areas drop off, and I get something along those lines. Okay, do the same thing in the y direction where I have tau x prime y prime times a, and then again all of these forces at different angles as I have written here, and you can go through that on your own. And then solving for tau x prime y prime, we get something like this. Now we just massage these equations a little bit more, do a little bit of trigonometry, a little algebra, and we get an equation here for sigma in the x prime direction based on sigma x and sigma y and tau. Okay, and then through the same process, I could find what's going on in the sigma y direction just by cutting at basically a 90-degree angle from where I am right now. I can find sigma y prime, which would be of something of interest. So it's the same approach as above. Okay, and then my tau is given by this. So this is how I can find what the stresses are oriented at an angle of theta from the original state of stress that I'm given. So that's how I do basic stress transformations. Okay, we'll do the same thing for strain transformation. So we're going to look at normal strain first. So again, my strain is right here, which is defined as the strain times the original dx. And I'm going to break that strain up into my new x prime and y prime conditions based on sine and cosine of the angle, the new angle that I'm looking at. I do the same thing in the y direction. Again, I have this strain in the y direction, which I can break up into x prime and y prime components based on a sine and cosine of theta. I also get some strain from my shear strain, and remember my shear strain is the change in the angle. Okay, and by the arc length, that this length right here is that shear strain times dy. Break that guy, which would be in the x direction, break that guy up into the x prime and y prime directions as given here by, again, a sine and a cosine. Okay, so my dx prime, okay, looking at here, again, this is my new orientation. I've got to keep in mind that that dx prime is essentially dx over the cosine of theta, or dy over the sine of theta, just by this orientation that I have right here. Okay, my delta x prime is basically each component in the x prime direction. So I have this little piece here, which is epsilon dx cosine, and then I have epsilon dy sine, and then I have the gamma dy cosine. Okay. Now, by definition, the strain in the x prime direction is delta x prime over the initial dx prime that I found previously. So basically dividing these two, I get something that looks like this for the strain in the x prime direction. Okay. Then using the same trig identities and things, I can find the strain in the x prime and the y prime direction given by this equation. Notice this looks mighty similar to the previous equation on the previous slide for stress. It's the only difference being instead of tau, it's actually gamma over 2. Okay, whereas all the sigmas go directly to epsilons, going from stress to strain. Okay, but it's the same general form. It's just there's a factor of 2 in the shear part. Okay, now let's look specifically at the shear strain. So again, shear strain is a change in angle, right? So I'm going to start with finding delta y prime, which again is this line right here, which is essentially equivalent to all of the changes in the y direction. Okay, so again, I've got my y component here, x dx sine theta, epsilon dy cosine theta, and then gamma dy sine theta. Again, that's my change in y prime, adding up all of those components. Therefore, my alpha is essentially that delta y divided by delta x. Again, that gives me the angle alpha that I'm looking for. So again, taking this delta y and dividing it by what I know delta dx prime to be, I get an equation just like this. Okay, I can do something similar for the beta, which is over here on the dy. I won't go through that, but I get something similar. Some of my signs change. I get a negative sign over here. Okay, but it's the same general idea for beta. Okay, and by definition, my shear strain is basically the change in the angle, so it's basically alpha minus beta that I have here. So I get an equation like this, and then through some trig identities and whatnot, I get my shear strain transformation at a different angle, just like this. Again, everything's the same as in the stress, other than the fact that I've got my strain divided by 2. Okay, but it's the same general form of the equation. Now, the real reason we want to do this is we generally want to find our maximums. Okay, because the way we orient might not actually be where the maximum strain is. So I want to find where the maximum normal stresses, strains, where the maximum shear stresses and strains are. So what I do is I take a derivative of that equation, set it equal to 0. That gives me the orientation of the what we call principal axis, where sigma x, sigma y are at their maximum. Okay, and that orientation is given by this equation here. Okay, so that's the principal, okay, which is the maximum shear, or I'm sorry, the maximum normal stress given by this equation. Now, I have two stresses here, 1 and 2. Okay, 1 by definition is bigger than 2, so that would be plus all of this stuff, versus sigma 2 would be minus all of this stuff. And again, I get this just by plugging in my principal angle into the equations I had previously. Now, when I'm in my principal stresses, my principal normal stresses, there is no shear going on. So those are the only stresses. I just have normal stresses in the principal case. Okay. Now, looking at the maximum in-plane stress, I do the exact same thing, take a derivative, set equal to 0, and I find that my shear angle, my maximum in-plane shear stress, is given by this, which you will find is actually 45 degrees from the principal direction found previously. Okay. Once you find that, you can plug it into the equation. You can find your maximum in-plane shear. Now, with the in-plane shear, you do have normal stress, and they're basically the same in both directions. So we take essentially an average, sigma x over sigma y over 2. And again, these two equations just come from taking this angle, plugging them into those equations we developed in the first slide. I can do the exact same thing with strain. Okay, and it follows the same idea. Again, it looks very similar to what I have over here. Again, the only difference is this, the shear is divided by 2 when I'm talking about strain versus stress. Okay, so that's for the principal strain. Same idea for the maximum in place shear strain. Okay, I can find that shear angle, plug that in, I get an equation that looks very similar to what I have for stress. Again, just the shear being divided by 2. Now, These, again, are probably the most important equations on this slide, because this is where the maximum is occurring, and this is how, when you're designing something, you're interested in where the maximum is occurring. Okay, but if you want to find a specific angle, you can use those equations developed in the first two slides.